Okay, so this is the key to the 5 practice problems that are similar to those on the final exam. So in the first one, and this is topic 24, it says work is required for some parts of this problem. Show all required work to receive all points. And this problem has 3 parts. Okay, so so you have this polynomial function, and I'm gonna go ahead and rewrite it over so you'll see it better. So your polynomial function is this cubic function, which is x cubed plus 5x squared plus 2x minus 8. And the first thing you want to do is to list all possible rational roots of this polynomial function. Now remember, it's asking for the possible rational roots. All right, so the possible. So to find the possible rational roots of a polynomial function, you're basically going to look at the quotient of the factors of the constant term. So I'm going to write it like this: factors of -8 divided by the factors of the leading term. So the factors of leading term, which is in this case +1. So the factors of -8 are plus or minus 1, plus or minus 2, because +1, -1, +2, -2 all go into -8 evenly. Um, so the um, so the factors of -8 are plus or minus 1, plus or minus 2, plus or minus 4, right? 4 goes into 8, -4 goes into -8. And then itself, plus or minus 8. So those are the possible rational zeros. Okay, so that's going to go here: plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So altogether I have 2, 4, 6, 8 possible rational zeros. Okay, now remember, your the degree of this polynomial is 3. So the most you can have is 3. All right, but they're saying that if you have 3 rational zeros, then it has to come from these possible rational zeros. And so that's where the next part comes in. So then you're asked, all right, so use synthetic division to find an actual root. Now make sure you follow directions. The direction says use synthetic division. All right, so you have to use synthetic division. And so to use synthetic division to find an actual root, you're going to use that format that you've learned before. All right, so we're going to pick one of these possible rational zeros. So let's suppose you chose -1 as a possible rational zero. Now remember, the numbers that go here, right here, are the coefficients of your variable, of your terms. So and it's got to be in descending order. So 3, 2, 1, and your constant. So it's 1, 5, 2, -8. 1, 5, 2, -8. Okay? So then remember, the next step to do is you bring down the first number. So you bring that down, then you multiply by this possible rational zero. So -1 times 1 is a -1. Put that here. Then you add. 5 and -1 is 4. Then you multiply again. -1 times 4 is -4. Then you add. 2 and -4 is a -2. Then you multiply. -1 times -2 is +2. And you add, you get 6. So my remainder is 6. Now remember, in order for it to be a root, then that remainder has to be 0. Okay, your remainder must be 0. So -1 is not an actual root. So we're going to try another one. So let's try +1 in this case. So let's see if 1 works. So let's try 1. And we're going to list the numbers again: 1, 5, 2, -8. So I'm trying to get a remainder of 0. So bring down the 1. 1 times 1 is 1. You add, you get 6, right? 1 times 6 is 6. Add, you get 8. 1 times 8 is 8. Add, you get 0. Hey, there we go. The remainder is 0. So one of your roots is +1. So x equal 1 is a root. Okay? Now, remember Then, okay, so use the synthetic division to find an actual root. Okay, I did. All right, I did. Now, part 3 says this. Part 3 says use the quotient from part 2. So that's this right here. That's your quotient. So we're going to look at that polynomial that represents this now. So there's your quotient. That's your remainder. So my quotient, remember, if this is x cubed, then this is going to be x squared. So x squared, x, and your constant. So my quotient then becomes x squared plus 6x plus 8. All right, so I'm going to use this quotient to find the remaining roots. So basically, I'm going to factor this, and if I'm going to find the remaining roots, I'm going to set that equal to 0. So I'm going to take that quotient, I'm going to set it equal to 0 to find the remaining roots. And for us, this is going to be factorable. So when I factor this, I get x plus 4, x plus 2. Then I'm going to set each factor equal to 0. So when I set each factor equal to 0, I get x to be negative 4 and x to be negative 2. So those are your other roots, negative 4 and negative 2. Okay? So remember, you had degree 3. So since I had degree 3, the maximum number of um, rational zeros I can have would be 3, and I do have 3 of them. 1, negative 4, and negative 2 are rational numbers. But now you got to answer the last question though. So I want you to factor this function. Well, if 1 is a 0, if 1 is a root, then that means that so that means that f of x is going to equal, so that means one of your factors will be x minus 1, right? X minus 1. In fact, that kind of makes sense because when I set that equal to 0, I get x to be 1. If your other root is negative 4, then the factor has to be x plus 4, right? And then if your other 0 is negative 2, then the factor has to be x plus 2, because that's how you got negative 2, by setting that x plus 2 equal to 0. And there's your answer. So it's a product of these factors. So that was number 1. Number 1. Not that difficult. The main part that some students mess up on when doing a problem like this is they don't use synthetic division. They just go ahead and factor this some other way. This is not factorable by grouping. If you group these two and group these two, it's not factorable. So follow directions, because if you had followed directions, one of these right here would have been um, an easy one to use to get a remainder 0. But before we go on, remember these are your other zeros, right? So negative 4 and negative 2, there's negative 4 and there's negative 2. Okay? All right, so that was number 1. All right, so let's look at number 2. So number 2, you want to solve this exponential equation. So that's an exponential equation. The variables are located in the exponent. And you want to do this by getting the bases to be the same. And so we can here. Those are easy to do. So don't use logarithms. The idea here is for you to get the bases to be the same. Okay? So if I look at 9, if I look at 27, we all know that 9 is 3 squared. All right, so here's my base. My base here is 3. That's my base, 3. So what I want to do is try to get 27 with that same base. And I can, because we all know that 3 cubed is 27. So I get the bases to be the same. So I'm going to come here now and I'm going to rewrite 9, and I have to see this. I have to see that you said 3 squared, all raised to the 3x minus 1. See, that 3 squared is just 9. And then I need to see that you rewrote 27 as 3 cubed. So 3 cubed to the x plus 6 power. And now what we're going to do is use the fact that you have a power raised to power. So I'm going to multiply these exponents. So I get 3 raised to the 2 times 3x minus 1 equals 3 raised to the 3 times x plus 6. And then I can use the one-to-one property of exponents. So since the bases are the same, the exponents have to be equal. So that's that one-to-one property. So then that means that 2 times 3x minus 1 must equal 3 times x plus 6. And then notice I have this very simple linear equation. So I just distribute and I solve for x and I'm done. So I get 6x minus 2 equal 3x plus 18. Subtract 3x from both sides. 6x minus 3x is 3x. Minus 2 equal, and then that's 0 here. I get 18. Add 2 to both sides. I get 3x, combining like terms, that's going to be 20. Divide both sides by 3. I get my solution to be 20 thirds. Okay, so that was number 2. Not that difficult, fairly easy to deal with. Okay, so in number 3, which was topic 31 in our course, you want to use one of the following 3 properties of logarithms to let's say, expand this logarithm. All right, now remember it says show work, so you have to show your work. Don't just write the answer. Show all required work. So what you had to do first was notice that you have this quotient here, right? So I'm going to use the quotient property of logarithms. So I'm going to use this property first. So according to this property, according to the quotient rule for logarithms, I can rewrite this as, and I had to see this is what you had to show, log base 4 of 4x minus log base 4 of y to the ninth. Okay? Then you have to go further. See, now you're taking the log of a product. That's this right here. So I'm going to use a product rule. So when I expand this part here, I'm going to write this as a sum now. So that becomes the log base 4 of 4 plus the log base 4 of x minus, and then this one here, this logarithm, you see that exponent? I can use the power rule for exponents. So I can take this power and bring it out in front of that logarithm. So this becomes 9 log base 4 of y. Okay? And then the next thing to do is to remember, see this right here? I can even write this further. So it says, where possible, evaluate logarithmic expressions without using a calculator. So you see that log base 4 of 4? So if you think about it, remember if you change this to an exponential, 4, the base, raised to what power? 4 to what power is the argument, which is 4? Well, 4 to the first is 4, right? So this is 1. So I get 1 plus log base 4 of x minus 9 times log base 4 of y. All right, and that is it. There's your answer. So 1 plus log base 4 of y minus 9 times log base 4, x, and then minus 9 times log base 4 of y. Okay? So there's the work you had to show. You had to show this. Okay, now number 4. So number 4, you want to solve this log equation. So you see you have an equal sign, so you have this log equation. So you're going to find the solutions. And so if you notice this is an addition, so you're adding 2 logs. All right, so that's going to be this one here. So you're gonna condense this into one logarithm. So let's think about this. So the log base 2 of x plus the log base 2 of x plus 4, I can write as a product. So that's become the log base 2 of x times x plus 4. And that's equal 5. So I wrote the sum of these 2 logs as one logarithm using this one. All right. Now I'm going to change this to an exponential. So you're going to say 2 to the 5th power, 2 to the 5th power equals the argument, x times x plus 4. And 2 to the 5th power is 32 equal, and then I'm going to distribute this, that's x squared plus 4x, right? And I'm going to go ahead and transpose the 2 sides. So when I transpose the 2 sides, I get x squared plus 4x equals 32. And then notice I have this quadratic equation, so I'm going to bring the 32 to the other side. So I get x squared plus 4x minus 32 equals 0, and this is factorable. So when I factor this, let's see what I get. I get x plus 8 times x minus 4. Yep. So I get x to be negative 8 and x to be 4. Okay. Now remember though, you can when we talked about logarithms, you can only take the log of a positive number, right? So your argument cannot be zero because the log of zero is undefined, and also the log of a negative number. So so you have to check to see if any of these proposed solutions, we call these proposed solutions, if any of these proposed solutions are actual solutions to this equation. So right away, see that's negative 8? You know that negative 8, you cannot use that. You know that negative 8, even though negative 8 is a solution to this quadratic, it's not a solution to this log equation, because if you let x be negative 8, you're taking the log of negative 8, and that's undefined. And even if you put negative 8 here, negative 8 plus 4 is negative, so you get negative there as well. So I know I cannot use negative 8. But look at 4. So when I substitute 4, this argument is still positive. 4 plus 4 is 8, and 8 is still positive, so we should be good. So the only solution, your only solution is x equal 4. That's the only solution. So I'm going to put 4 here. Okay? But there's the work. There's the work. You have to show that work. And then finally, I think the last one, yeah, the last one is number 5. And basically, you want to graph this exponential function. And there are 6 parts to this. And so the first question is this: is this function a polynomial, a rational, exponential, or logarithm? Actually, well, obviously you see it's not a logarithm because there's no log there. You know it's not rational because you don't see any any variables located in the denominator, right? And it is not polynomial because the variable is located in the exponent, so that makes it exponential. So this is exponential. Then you want to indicate the horizontal asymptote. So remember, the horizontal asymptote, all exponential functions have a horizontal asymptote. That horizontal asymptote is that constant. In this case, negative 5. Not 5, negative 5. And the horizontal asymptote is a horizontal line. So you got to name it y equal. So that's y equal negative 5. Okay? Then you want to indicate the domain of this exponential function. Well, the domain of all exponential functions is all real numbers. And you want to put this in interval notation, so negative infinity to infinity. And then you want to indicate the range. Now, the way I would do that for the range is this. I would think about, all right, so I know that my horizontal asymptote is y equal negative 5. So here's y equal negative 5, let's say, right? Okay. And I know that the graph, since this is positive right here, I know that the graph is going to be above the exponential, I'm sorry, it's going to be above the horizontal line. And since 3, the base is greater than 1, it will be increasing, something like this. And so even if you've messed this part up here, you know the graph is above. So you know that the range will be from 5 to infinity. But remember, you got to be careful. This is a horizontal asymptote, a dotted line. The graph gets closer and closer and closer to that horizontal asymptote, but doesn't touch it or cross it. So that's why we're going to have to use parentheses here. So it's parentheses negative 5 to infinity. And then the y-intercept's easy. To find the y-intercept, you just let x be 0. So we're just going to let x equal 0. So when I let x equal 0, I get y equal 3 to the 0 minus 5. 3 to the 0 is 1. 1 minus 5 is a negative 4. So my y-intercept is negative 4. And so then you want a graph. And that's easy to do. Now make sure it says plot about 3 points, okay? So make sure you do that. And then it also says show the horizontal asymptote as a dotted line. So let's go ahead and do the horizontal asymptote. So you know it's y equal negative 5. So I'm at negative 5 right here. I'm going to draw a dotted line. Okay? I also know one of my points. One of the points on the graph is this y-intercept, so negative 4 right here, right? And now all I need is 2 more. So there's one of them. I need 2 more. So let's use the t-table. So, and remember, here's my function, y equals 3 to the x minus 5. So if x is, let's say, 1, if x is 1, I get 3 to the first minus 5, right? 3 minus 5 is a negative 2. So when x is 1, my y value is negative 2. So 1, -2. So there's the other one. All right, now remember, it says to draw 3 points. All right, so at least three to make it look like a good exponential function. So let's do 2 then. If x is 2, I get 3 squared minus 5, right? And 3 squared is 9. 9 minus 5 is 4. So I plot the point 2, 4. So 2, 4 is here. And that's about all I need. So I know, remember, the graph goes towards the asymptote like this. Don't make it look like it touches or crosses. Just that's fine. Just leave it like that with an arrow. And on this side, it rises very rapidly. Something like that. And there's your function. Okay, so those are a quick review of the last part of the last few weeks, I guess, of this course. So just make sure you understand this because you can see these on your final exam. All right, so that's the end of the review of these problems.